Greetings, my fellow electric monkey brains. Today I'm going to show you how to make this very cheap and simple current probe. It's just a ferrite core. This is actually a metal iron powder core wrapped with several windings, and those windings are soldered onto this very small piece of board in parallel with this socket into which I can place different resistors, so that the resistor and the inductor are connected in parallel. The way this works is that I would take the wire in which I want to measure a current and I'd pass it through the core like this. And then I would attach my scope probe and measure the voltage across this resistor. And the voltage across this resistor is proportional to the current in the winding. The current in the winding is proportional to the magnetic flux in the core, and the magnetic flux in the core is proportional to the current of the wire which is passing through the center. So that's the way it works. So let's take a look at a diagram to explain why I put a resistor here on this. Okay, so I've drawn here a diagram of a wire carrying a current, and it produces around the outside of itself this sort of spiraling magnetic field. Well, if we were to place our ferrite core around that wire, we could capture that magnetic field, and then it becomes a flux inside our core, and then if we put some windings around it, we can generate a voltage in that winding. Now, you may or may not know that if we do it this way, we can only measure AC currents because this works by induction. That means this current has to be changing in time in order for a voltage to be generated here. And you can't measure DC currents with this type of current probe. But that's okay because the voltmeter, any basic voltmeter, is very accurate when it comes to measuring DC currents, so we don't really need that. But this whole situation is actually like a transformer, which I've drawn over here, where the wire in which we're trying to measure a current acts like a single turn of a primary on a transformer. And these secondary turns would be the windings which I put around there. And then that would generate a voltage which we measure. And you can see here that I've connected a resistor in parallel with that. So the question is, why do we need this resistor here? The answer is to do with the fact that inductors and capacitors have voltage and currents which are out of phase with each other. So what does it mean in our case? Well, it means that in our secondary winding, the voltage and current will be out of phase. The current which we try to measure produces a magnetic field which is in phase with it. And that magnetic field in the core produces a current which is also in phase with it. But we measure a voltage which is out of phase. So we need to bring this voltage in our inductor into phase with the current in it. And we do that by placing a resistor in parallel with it. As long as the resistance of the resistor is much smaller than the impedance of the inductor, it will bring down the voltage in the inductor and also force the voltage in the inductor to be in phase with the current in it. Then when we measure the voltage, we can be sure that this voltage is in phase with the current we're trying to measure. Okay, so when you come to design this thing, there's going to be three main things that you want to think about. First is what type of core you want to use, then how many turns and what value of resistor do you need, and finally, last but not least, is the calibration. So if we turn to the core, basically you have two choices. One is a pure ferrite core and the other one is a metal iron powder, which is what I used. Now the ferrite core has a very high permeability. That means that when you place it around the wire, it will capture more of this magnetic field, producing more of a voltage for less turns. It means that it will be very good for measuring small signals. In addition, the pure ferrite has much lower loss, so that can help, and it also has a higher frequency range, so it can be measured. It's good for measuring small signals at a broader bandwidth. But because it has a high permeability, it also means that it will enter saturation more easily. So for example, if the current which is passing through our wire is quite high, for example, 5 or 10 amps or even more, this core could pass into saturation, and we want to try and avoid that. So the metal iron powder core is a better option for high currents because it has a lower permeability and it will become saturated less easily. Now you may be thinking that this type of core or design is absolutely no good at all because the wires in which you want to measure current are all soldered onto your circuit and you can't get to them and things like that. Well, in that case, one of these type of designs might be useful. This is actually a choke. It has two ferrite half cores inside, and it's designed to clamp like this over a mains wire, and it's to stop high frequency signals coming from, example, your power converter back into the mains by creating this type of high impedance line. And all you have to do is wind some windings on here, attach a resistor, and then clamp that around the wire that you want to use. And then that will act in exactly the same way as this one which I designed. So that can be quite useful. Now the next consideration is the number of turns and resistor. Well, basically it works like this. The more turns you put on, the more signal that you will get out. And that means that will be better for measuring smaller signals. And the value of the resistor really depends on the amount of turns, because the more turns you get, the more voltage you will get, and you need to bring that down with a resistor. So the answer is basically design it and test it for your particular application, and then you can redesign it later. For me, I measure currents from about 20 milliamps up until about 4 amps, from frequencies of about 1 kilohertz up to a megahertz, and this works absolutely perfectly for that. And it's a metal iron powder core. It's got about 30 turns on there roughly, and this is a 25 ohm resistor on here, and that works just fine. So you can use that as a rule of thumb. Design it and then redesign as you like. So last but not least is the calibration. So why do we even need a calibration? Well, it's obvious. It's because what we measure at the end of the day is on the scope is a voltage, but what we really want to measure is a current. So we need some way to convert this voltage into a current. That's what calibration is. The way the calibration works is that we pass a current through our wire, which we know already. So we know it already, which means we have to use another device in order to measure this current or to calculate it. And then because we know this current and we know this voltage, we can find the constant of proportionality between the two. That means just a number which we need to multiply our voltage to in order to get our current, and that's a calibration. So lastly is the question of loading. What is loading? Loading is, well, it's like a transformer. If I have many turns on my output here, it's going to draw energy from this primary. It means that the more turns I put on, the more energy I'll draw. And if I draw a lot of energy from here, it's going to pull more current. So it's like I'm changing the current in the wire, which I'm trying to measure by the virtue of measuring it. So you need to try to avoid loading. But one way to get rid of the loading is to calibrate it out. However, it's a good idea to try and avoid it in general. So you're always going to have a tiny bit of loading, but a small amount of loading can be calibrated out. If you have too much loading, for example, if you use a ferrite core and you put not one layer, but 3 layers of windings around it, and then you try to measure 5 amps, and then you put a 10 ohm resistor on here, which is only a quarter watt, it may end up burning that resistor. If you have a quarter watt resistor on here and you burn it, it means you have too much loading. I've never done that, but it could be possible. So it's just something to watch out for. So now I'm going to go through the calibration process which I use, and it's not the only calibration process that you can use, however. Okay, so how do we actually calibrate our current probe? Well, I'm going to show 2 methods of calibration today. The first one I've drawn here. It requires a function generator to be attached across a capacitor of known capacitance. And then we can measure the voltage across that capacitor VC with our scope. And then we can use Ohm's law here, which I've written here, to calculate the current which is passing in the capacitor. We assume that the capacitor has 0 resistance, which is a good approximation in practice. And then the impedance of the capacitor just becomes the reactance of the capacitor XC. And the reactance of the capacitor is 1 over 2 pi f multiplied by the capacitance. And so we can calculate this current that's passing through the capacitor here. And then once you have that value, that's the current which is also passing through our current probe here, with which we measure a voltage VI. So then we can write this equation and we can say that the voltage which we measure, if we was to multiply that by some number, then we would get our current. And we call that unknown number x, and that's our calibration constant. So if we solve for x and then calculated, I actually previously did this and I got a value of 2.749, and then that's our calibration constant. What it means is that we can take this number, this calibration constant, and anytime we measure a voltage on the probe, we simply multiply it by this number and we directly get the current which is passing through it. This is called a calibration constant because it's assumed to be constant. In reality, it's not constant, and it can change over frequency and power levels, meaning the amount of current which is passing here. So if you was to do this professionally, you would absolutely have to measure this value over different frequencies and power levels. So let's take a look at this on the bench and discuss the practicalities of it. Okay, so here's the setup of our first calibration method. Here I have the function generator. It's connected directly to this 12 nanofarad capacitor, across which I'm measuring the voltage in red. The green probe is connected to the current probe and it's measuring the current. And here on the screen you can see that the current in green is actually behind the voltage in red, which is exactly what we expect for a capacitor. Now what I would do to measure this is to freeze the scope, so the scope has now taken a measurement, and then I would use the cursors on the scope to measure the peak voltages and such, and then I would use those values in the equations which I showed previously to get the calibration constant. Then I would change the frequency on my function generator, go to some other frequency, and I would repeat the process and get a new calibration constant. And I would do that for several frequencies. Now, if the calibration constant is different for different frequencies, it means that you have an error in your system, and there's a good chance that that error is coming from this capacitor. Now the reason is that the value of most capacitors is not constant. As you change the frequency, they can have a range of capacitances. So it really depends on the quality and type of capacitor you're using, but in general, putting a capacitor into the calibration system introduces a source of error into the whole system, especially as you change the frequency. So in order to remove this capacitor and therefore source of error in the calibration process, I'm going to show you a different type of calibration next. Okay, so this is the second calibration method which I'm going to show. I've never seen anybody do this before, but it's actually to use a DC to DC converter for the calibration process. Here I've drawn a boost converter, but essentially you can use any type of converter. If you don't know how a boost converter works, I'll post a video link above. Essentially, when the switch opens, it pulls current through this inductor, which stores energy, and then when the switch closes, that energy is then funneled off into the load. Our input current for this device is going to be in the form of DC, which means it's flat over time. That's very good for us because a DC current is very easy to measure. That means that we can assume that this current measurement from the power supply itself is fairly accurate. Now when we look at the diagram, we see that all of the input current is actually going to pass through our current probe here. This enables us to be able to equate this voltage that we're going to measure with the input current and then find our calibration constant, and our calibration constant will allow us to convert this voltage which we measure into a current, thereby calibrating our current probe. The problem which we have is that when we measure this current here, we're going to see these pulses because the current coming through this line is in the form of pulses. So we see these sort of triangle shapes here. But in order to equate this voltage to our current, we need to find the average value of these pulses. And to do that, all we have to do is to find the area underneath the line. And that means that if we look at this pulse, it's like a triangle which we can split into two right-angled triangles here, which I've labeled 1 and 2. So to find the area, we just multiply the time here, which it's on, by the peak voltage. And the peak voltage and the time which it's on, it's very easy to measure those values with the scope. Then we get the area of triangle 1, and then we do the exact same for the triangle 2. Then we add the 2 to get the total area, and then we write here the total area, and then we divide that by the time period. And then that will directly give us this average value here, which we want to find. And then we do the same as we did in the previous calibration method, which is to equate this value of voltage and multiply it by some unknown, which is our calibration constant, and then we equate it to the input current. And then we solve for x, and by taking all the measurements, which I did previously off camera, and then I ended up with 2.531, which is, you can see, is quite similar to the value which we got from the previous calibration method using the function generator. So I'm going to put all this together on the bench again, and then we can discuss the practicalities of it. Okay, so this is the second method of calibration which I'm going to show using a DC to DC converter, boost converter. Here on my circuit board, all of this circuitry from here to here is not being used. I'm just using this chip here to generate a pulse. I can control the pulse width with this potentiometer, and I control the frequency with this one. The pulse is then sent to this MOSFET here. Current comes into the device through this yellow wire into the inductor, and then through this blue wire into the MOSFET. When the MOSFET switches off, the energy in the inductor is passed through this diode and dissipated in this 820 ohm resistor and 20 microfarad capacitor. The value of the diode, resistor and capacitor are irrelevant, they're just there to be able to dissipate the power. The red probe is measuring the voltage on the MOSFET, and the green probe is measuring the output of our current probe, which we're trying to calibrate. Now, by far the most important component here is the inductor at the back here. This inductor, we want it to behave in a linear fashion. So what does that mean? Well, let's turn on the power and then take a measurement here and freeze the scope, and then I'll turn off the power supply because I don't want my components to get hot. The green trace is the current, which is we're measuring through the inductor, and we're measuring it via our current probe. And we can see that these lines here on this triangle are quite straight. That means that our inductor is acting in a linear way. If these lines were curved, it would mean that we are almost saturating our core, and we're entering into a non-linear response in its behavior. We want to avoid that. We want these straight lines on this triangle here, because that will make our calculation of the area of this triangle more accurate. So in order to make these measurements here to calibrate our current probe, we're concerned with two measurements. One is the current on the scope, and the other one is the current which we measure on the power supply. Now, it's important to remember that the board itself and all the chips consume current. So first we have to measure this tiny current or quiescent current, and then subtract that later from the main current which we're going to measure. In order to do that, all we have to do is disconnect these power lines here from the power components. Then our board will not be consuming any large currents or power, and only the chips will be consuming power. And then we measure that current. I measured it before, it's about 34 milliamps, and then we can subtract that from our main current measurement. So when we want to measure the current, obviously we have to turn it on. So we turn it on, we look at the current here, it's 850, 860, 865, 860. It's going up. Why is it going up? It's because the MOSFET's getting hot, basically. So in order to deal with this, you can either put a heat sink on your MOSFET, or you can do something which is called taking averages, and that means that you take multiple measurements of that current and then take an average value and use that and pretend that that's accurate. So you can do either one that you want yourself. So then you can measure that current, and then don't forget to take away the quiescent current of your circuit board from it. So then we would turn to measuring the current on our scope. In order to do that, I would switch on the power, and then I would make sure that I get in the shot two current pulses. Here I have one current pulse and the beginning of another one. Then I would freeze the scope, turn off the power supply so nothing gets hot. Then I would use the cursors to be able to calculate the area underneath this green current pulse, and then I would put that into the equations which I showed in the previous diagram to be able to calculate the average part. Now, one more thing about this method using a DC to DC converter is that you want to make sure that your boost converter is operating in a discontinuous mode. Discontinuous mode means that there is a point in time where nothing is happening, it's completely dead. That's here. And that means that our current pulses are separated in time. That makes the calculation of area underneath the current pulse more easy. If we were operating in a continuous conduction mode, then these two current pulses here would be overlapping, and that would complicate the calculation of the area underneath the line. So that's all there is to say about this, I think. I hope you learned something from this video. If you'd like to support the channel, you can do so using the links below or simply subscribing. Thanks a lot.